Dear students, after studying this module, you shall be able to know about NGP or neighboring group participation, learn reaction mechanism of NGP reaction, identify the stereochemistry of NGP reaction, evaluate the factors affecting the NGP reaction, and analyze phenonium ion, NGP by alkene and NGP by heteroatom. Now students, in the entire module, I will prefer using NGP as a short form of neighboring group participation. The reaction center, that is the carbanium center, has direct interaction with the lone pair of electrons of an atom or with the electrons of S or P bond contained within the parent molecule. But these are not in conjugation with the reaction center. A distinction is sometimes made between N, S and P participation. A rate increases due to NGP is known as enchimeric assistance. Synartectic acceleration is the special case of enchimeric assistance ascribed to participation by electrons binding a substituent to a carbon atom in a beta position relative to the leaving group attached to the alpha carbon atom. According to the underlying model, these electrons then provide a 3-center bond or a bridge fastening together, as the word synartectic is intended to suggest. The alpha and beta carbon atoms between which the charge is divided in the intermediate bridge ion form and in the transition state preceding its formation. Now let us understand a little bit more about NGP participation. Neighboring group participation is observed in nucleophilic substitution reactions where a neighboring group helps in the removal of the leaving group to form a reactive intermediate that leads to the formation of the product. Increase in the reaction rate and unexpected stereochemical outcomes are associated in reactions involving neighboring group participation. An atom having an unshared pair of electrons and is present on the beta position to the leaving group can act as a neighboring group. Also, NGP is mostly observed in solvolysis reactions where the solvent itself acts as a nucleophile. Now, for example, take a look at the figure here. During NGP, the neighboring group G, as shown here, attacks the electrophilic center to eliminate the leaving group L. Now, this leads to the formation of a cyclic intermediate which is very reactive. The nucleophile, represented by Nu minus, then attacks this intermediate to form the product. If the attack takes place on the carbon that was having the leaving group, then the configuration will be retained because the configuration on that atom will be inverted twice. Groups like halides, hydroxides, ethers, thioethers, amino groups, carboxylates, phenyl group, pi bonds, etc. have been identified to act as neighboring groups in many reactions. Thus, students, according to the IUPAC, NGP is an interaction of a reaction center with a lone pair of electrons in an atom or electrons present in a sigma or a pi bond in organic chemistry. When NGP is in operation, increase in the reaction rate is normal. It is possible for neighboring groups to influence many reactions in organic chemistry. For nucleophilic substitution reactions, NGP is defined as the introduction of a new reaction intermediate by a substituent that bonds to the reaction center. For such substitutions, NGP occurs primarily in the form of intramolecular nucleophilic attack followed by intermolecular substitution. Some nucleophilic aliphatic substitution reactions that are overall intermolecular in nature evidently begin with the nucleophilic atom in the substrate reacting intramolecularly with the carbon atom bearing the leaving group and finally expelling the leaving group. The resultant intermediate then reacts with the external nucleophile, giving the observed substitution product, which is an intermolecular nucleophilic substitution. Now, to explain this better here, we should have a look at this figure. The role of the nucleophilic atom in the substrate in the overall reaction is known as neighboring group participation or enchimeric assistance. The net reaction is a nucleophilic substitution in which A is the substrate and B is a substitution product. Now, you can see clearly in this figure what is A and what is B. If the reaction were to proceed via SN1 mechanism, it would yield B as substitution products and with retention of configuration at the chiral center and its enantiomer C with inversion of configuration. Now, you can see this more clearly here in this figure. If the reaction were supposedly to proceed via SN2 mechanism, it would occur with the inversion of configuration at the chiral center, yielding C as the only substitution product. This is also clearly shown in the figure. As you can see, the formation of B as the only substitution product indicates that the reaction is not a simple intermolecular nucleophilic aliphatic substitution that follows either SN1 or an SN2 path. Neighboring group participation is invoked to explain the course of this reaction. Now, there are some conditions, students, for NGP reaction when it is in operation. Number 1 is that it is normal for the reaction rate to be increased in case of NGP, that is neighboring group participation. Number 2, it is also possible for the stereochemistry of the reaction to be abnormal or say unexpected when compared with a normal reaction. Now, let us consider some more aspects of neighboring group participation. First would be NGP by heteroatom lone pairs. A classic example of NGP is the reaction of a sulfur or nitrogen mustard with a nucleophile. The rate of reaction is much higher for the sulfur mustard and a nucleophile than it would be from a primary alkyl chloride without a heteroatom. Now, you can see how NGP is taking place in this reactant, which is a nitrogen mustard having a heteroatom, that is sulfur. The next example of NGP by alkene. The pi orbitals of an alkene can stabilize a transition state by helping to delocalize the positive charge of the carbocation. For instance, students, the unsaturated tosylate, as you can see in this figure, will react more quickly, that is 1011 times faster for aqueous solvolysis with a nucleophile than the saturated tosylate. Now, you can imagine how much the rate has increased in aqueous solvolysis. The carbocationic intermediate will be stabilized by resonance when the positive charge is spread over several atoms. This is shown in the diagram. As you can see how NGP is proceeding in case of this tosylate and how the carbocationic intermediate is stabilized. Even if the alkene is more remote from the reacting center, even then the alkene can still act in this way. For instance, while forming alkyl benzene sulfonate, the alkene is still able to delocalize and stabilize the carbocation by delocalization of the positive charge in the carbocationic intermediate. Now, this is clearly seen here in the figure. As you can see, even when the alkene is remote, it still stabilizes the carbocationic intermediate. Also, the increase in the rate of the SN2 reaction of allyl bromide with the nucleophile as compared with the reaction of N-propyl bromide is because the orbitals of the pi bond overlap with those of the transition state. In the allyl system, the alkene orbitals overlap with the orbitals of a SN2 transition state. Now, this is shown here in red and blue, that is, the overlap is shown with nucleophile and bromine here as red and blue colors in this figure. NGP by cyclopropane, cyclobutane or a homoallyl group. If cyclopropyl methyl chloride is reacted with ethanol and water, then a mixture of 48% cyclopropyl methyl alcohol, 47% cyclobutanol and 5% homoallyl alcohol, that is but-3-enol, is obtained. This is because the carbocationic intermediate is delocalized onto many different carbons through a reversible ring opening mechanism. Now, next we will consider the NGP by an aromatic ring. In a case of benzyl halide, the reactivity is higher because the SN2 transition state enjoys a similar overlap effect to that in the allyl system. Now, this is represented in the figure that you can see. An aromatic ring can assist in the formation of a carbocationic intermediate called a phenonium ion by delocalizing the positive charge. Now, here you can see the delocalization of the positive charge and through the intermediate called phenonium ion. Now, let us take an example of such a system and the NGP involved in it. When the tosylate reacts with acetic acid in solvolysis, then rather than a simple SN2 reaction forming the product B, as you can see here the figure, a 48:48:4 mixture of A, B and C plus D combined was obtained. Now, the mechanism which forms A and B is shown. Now, you can see how the acetic acid actually is attacking the required center and the product is being formed. The A and B are formed. Now, the neighboring group participation on SN2 reactions. Let us consider some points on this topic. For nucleophilic substitution reactions, the NGP is defined as the introduction of a new reaction intermediate by a substituent that bonds to the reaction center. For such substitutions, neighboring group participation occurs primarily in the form of intramolecular nucleophilic attack, followed by intermolecular substitution. Now, you can see here in this figure the NGP in bimolecular nucleophilic substitution. The result of this participation is the formation of a substituted product with the retention of configuration by opposing the inversion of configuration, which is typically associated with the SN2 mechanism. Hence, the mechanism of a reaction is changed. In addition to this, neighboring groups can also affect the stereochemical outcome of a particular reaction. If a neighboring group affects a reaction in such a way that the rate of the reaction is increased, then that neighboring group is said to provide enchimeric assistance. The background reaction is used to determine if the neighboring group is rate enhancing or not. It is usually the analogous reaction in the absence of the neighboring group. NGP has been observed for a wide variety of substituents. Beta halogens, one carbon removed from the leaving group, are a very basic example of NGP, and we are going to discuss that here. They form a cyclic halonium ions with the reacting center. Ions of this type are known for chlorine, bromine and iodine. Cyclic ions of this type are formed stereospecifically with the inversion of configuration. Formation of a cyclic iodonium intermediate like this I have stated is clearly shown here in the figure. Similarly, sulfides, amines, alcohols and ethers can be effective neighboring group participations. Like the halogens, these groups add stereospecificity to the reaction center. Unlike halogens, these groups do not have to be in the beta position in order to act as neighboring group and can therefore form cyclic intermediates of rings of various sizes. These groups mostly provide enchimeric assistance in addition to the aforementioned reaction where retention of configuration of products takes place. Take a look at this figure where you can see amines, sulfides, ethers and alcohols as participating neighboring groups and X is acting as the leaving group. Beta acetoxy substituents are also known to be neighboring participants, 5-membered cyclic species by bonding through the carbonyl carbon. The existence of acetoxonium ion 2 has been supported by trapping experiments in ethanol to give 4, as you can see what is 2 and 4 over here in the figure. These trapping experiments were important in showing that the reaction was not proceeding by a classical SN1 mechanism. The reaction produces 3, proceeds with the inversion of configuration, as you can see, once again yielding an overall retention of configuration of the product. Now you can appreciate acetoxy group as an NGP here in this figure. In addition, students, to substituents with lone pairs of electrons, p bonded systems have been shown to be participating neighboring groups. Beta phenyl groups form phenonium ions by donation of p electrons or pi electrons. The phenonium ion intermediate, as discussed before, has been supported by the stereochemistry of the final substitution products as an inverted configuration. Now students, you can see here how the phenyl group is acting as a neighboring group and participates in the NGP through this figure. NGP has also been demonstrated for non-conjugated pi systems. Perhaps the most famous example of pi bond neighboring group participation is that of anti-7 norbornyl derivatives. These derivatives were believed to participate via a pi orbital interaction. Though this interaction invokes a molecular orbital explanation as opposed to the nucleophilic nature of the neighboring groups, still the retention of configuration is observed in the substitution products as seen with previous examples. In other words, students, one observed only anti-substitution with respect to the double bond. Now you can see how the stabilization of norbornyl cation through pi orbital interaction is taking place clearly in this figure. Supporting evidence was provided for this type of cation versus a rapidly equilibrating structure by Gassman et al., who substituted 1-methyl group into the double bond and showed a significant rate increase, almost of about 13.3 times greater than the unsubstituted reaction for a similar substitution reaction. When they substituted a second methyl group onto the double bond, the rate increase was similar to that in the first substitution, that is 148 times greater than the unsubstituted reaction. Hence, the stabilization of the carbocation is dependent on both carbons in the double bond. If the structure of the carbocation were rapidly equilibrating between the two double bonded carbons, then we would have shown no rate increase by adding the second methyl group. Thus, students, the SN2 pathway is more favorable pathway in which displacement of brosylate is possible for compounds like H3CO, CH2, CH2 to the power of 4 OBS, that is the brosylate ion, and CH3O, CH2 whole 5 O brosylate. The internal displacement pathway leads to the formation of relatively stable 5 and 6 membered cyclic oxonium ions. As the chain length increases, the likelihood of cyclic oxonium ion formation diminishes and the rates approach to that of the reference case where only SN2 attack by formic acid is possible. Now you can see here what I am talking about clearly, more clearly in this figure. Now let us come to the study of NGP on SN1 reactions. The SN1 pathway leading to a primary carbocation intermediate is not as favorable as NGP pathway leading to a episulfonium ion intermediate, that is NGP with internal displacement, as we have talked earlier. Now you can see here in this reaction the normal product and the rearranged product. So what is the rationale, students? The rationale is the SN1 pathway leading to the formation of primary carbocation is not as favorable as an NGP which is involved, leading to this, you can see here, the episulfonium ion, which finally leads to the product. So you can see the importance of NGP here, students, how important it is in this mechanism and simply it is not taking place by SN1. The more favorable is the NGP pathway. Now let us study about neighboring groups and rearrangements. I would like to take some case studies here, students. Case 1. The exobicyclic tosylate undergoes solvolysis 1011 times faster than the endoisomer. This happens because the pi bond assists the formation of the carbocation, and the assistance is much better from the backside of the tosyl group. Now you can see how from the backside the NGP is much more favored. Let us consider case number 2. The trans tosylate undergoes solvolysis 1000 times faster than the cis isomer. The non-bonding electrons of the carbonyl group assist the formation of the developing charge, and again the assistance is much better from the backside of the leaving group. Now again you can see here the backside attack is much more favorable. Considering case 3, although primary cations are not formed in solvolysis reactions, neighboring groups can assist the solvolysis of a primary substrate in a synchronous step to form a stable carbocation. Rearrangement occurs in beta phenyl substrates because the phenyl group donates electrons from the backside, again to give a very stable cyclic phenonium ion, as is also discussed previously in this module. Now case study, the neopentyl system, another primary substrate, rearranges rapidly to give the product. Now the CH3 group here assists the formation of a charge in the cyclic ion to give the more stable tertiary carbocation. Now you can see here clearly how CH3 group is helping to give a tertiary and a more stable carbocation. Now case number 5. This shows the uncommon case of a vinyl cation that can be formed by solvolysis because of the good leaving group triflate. The phenyl group migrates to give a more stable benzylic type ion. Now you can see here how the more stable benzylic type ion is given, and this helps to proceed the reaction in a faster manner. Now next students, we will like to discuss some more examples of NGP, and they have also been previously discussed in the same module. Now here you can see again a chlorine substituted with a heteroatom participating in NGP in example 1. Here the oxygen atom in the second example is participating in the NGP. You can see the third example where tosyl as a good leaving group, and then it attacks from the backside to form a stable ion, the carbocation, which is again stabilized by delocalization in the phenyl ion, and then classical case of NGP again. The fourth example students is SN2 type reaction, where inversion of configuration is here, it is a non-NGP reaction. Here you can see how the reaction is proceeding in a non-NGP manner, and NGP manner SN1 reaction is seen here, where the reaction presence of hydrazine acetate, DMF and 2 hours at room temperature in the presence of cesium carbonate, trichloroacetonitrile, and within 2 hours at room temperature the yield is 64%. Now students, after having seen so many examples of neighboring group participation in different ways and different participation of different leaving groups in NGP, let us summarize this module. NGP is a useful tool for synthetic chemists. In SN2 reactions, retention of configuration of the reaction center can be obtained instead of expected inversion of configuration. Also, if the neighboring group helps stabilize the intermediate produced, in the rate determining step, the rate acceleration occurs. In the case study students, as we have taken, the effects of solvent polarity on the competition between NGP and SN2 direct substitution were addressed. It was observed that polar solvents increase the NGP. Use of polar solvents seemed to help stabilize the cyclic cation intermediate which was formed in the reaction. Also, the strength of the nucleophile was found to affect the reaction outcome. When strong nucleophiles were used, only direct substitution was observed. Now students, after having explained NGP in such a detailed manner, I hope you found this module very informative.